let's go ahead and take a look at a few other segment lengths that we can see in circles, this time not from chords, but from when we have either two secants that intersect outside the circle, or from a tangent and a secant that intersect outside the circle. We can still see a way that these line segments are going to be divided up in a very predictable way. So let's start on the left here looking at two secants. They both intersect at point G, and they pass through the circle, creating interior chords EC and DF. Now what we can see here, how this is going to work, and we'll prove this later, is this exterior piece of our secant here, so from C to G. And we also have the exterior segment of the other. We're going to be able to use those to help us set up an equation. We can see that the exterior segment of one secant, so CG, times the entire length of this segment, so from E to G, or G to E, however you want to think about that. Their product, and this is just like the one we saw with two chords, is going to be the same as basically the corresponding product from the other secant. So we would take the exterior, so from F to G, and multiply that with the length of the entire secant segment, so from D to G. And that's going to be true for any time we've got two secants that intersect outside the circle. So real quick, a little whole number example. If we know that this was 2 and this was 6, so from E to C was 6. So this is where we get caught up a lot of times. We'll see the product here is going to be 2 not by 6, but 2 times 8, because 8 is the length of the entire secant segment there. So that product is 16. So if I were to tell you that, for example, on the other secant chord, we had 4, and this might not be a nice number, we'll find out. We're going to have to try and figure out what F is going to be, FG. So let's call that X. We know that X times X plus 4 should be equal to 16. So again, here's the case where it's X, the exterior, times the entire length, X times 4. Now when we set those together, probably because I just made this up on the spot, we're not going to get any really nice answers here. Because when we FOIL that in, we get 16, or distribute that in rather, we get 16 equals x squared plus 4x. So 0 is equal to x squared plus 4x plus 16. Looking for two numbers that multiply to 16 and add up to 4, and that is just not possible. We got 1, 16, 2 and 8, 4 and 4, doesn't work. So we have to use quadratic formula on this to see if we can get any solutions for x. So we'll leave it at that, but that's how that would work. If we take a look at the right, we've got a tangent segment and a secant segment. And this is actually going to be a lot like the secant one. So if we take our tangent, we realize it only has an external piece. Right? There's no part of the tangent line that passes through the circle. Secant, just like before, has an exterior piece and the whole length. So we'll start with actually the secant piece. Just like before, it's going to be the exterior length, FG, times the entire secant length. So that would be DG. That product would be equal to the tangent product that we're about to set up. And we can almost think of like the tangent as a secant with the exterior length and the entire length being the same thing, if that makes any sense. So what that would mean is the exterior length of the tangent would be CG. The entire length of the tangent would be CG. So we'll often write that as FG times DG is equal to that tangent length squared. So there's our formula for the secant tangent. We had our formula over here for the secant secant. There's the formulas. We'll work a few examples next.